Welcome back to Chapter 10, where we're going to begin our discussion in 10.2, and we're going to introduce a topic on what we call parametric equations and plane curves, curves in the plane. And so the idea behind this is going to be to add more information to our functions than they previously had, allowing us to change and encode more things that become useful either in multivariable calculus or even here as well. And so just different ways to represent functions that could be beneficial. And one way to do that would be to represent a function parametrically, or using parametric equations. And so we'll start out with the normal way in which we represent functions. We'll remind ourselves something like y equals x squared plus 1, where you have a function in two variables, where one variable is what you call the independent variable. He is your free choice. And then the other variable then depends on the independent variable in some way. In this case, y is dependent, it depends on x, and once you make a choice of x, y then has to be x squared plus 1. That's the dependency, and that's how it's defined here. And in doing so, it creates a graph of this, right? A visual representation of this relationship, where choosing an x value gives you an output of a y value, and this picture represents that dependency, represents that relationship. However, while this is a great way to talk about functions and a great way to represent functions, a standard way to do it, we are kind of at a loss in terms of the amount of information we can get out of it. For example, if we're in a physics class and maybe we're concerned with the motion or direction of a particle traveling or a certain speed at which that particle travels, if I just tell you y equals x squared plus 1, that may give you the information of, okay, well then that's maybe the path the particle travels. It's traveling along this path. But maybe it does not give you a notion of direction. If I just give you y equals x squared plus 1, you don't know which way the particle is traveling on this path. There's no notion of direction if I don't say anything. And it's not encoded here naturally. And so we don't have a notion of direction. We also don't necessarily have a notion of speed. Now, if this represents the position of the particle, I agree the derivative is the velocity of the particle, but you're limited to the derivative of x squared plus 1. And what if the particle had a different speed along this parabola? How would I encode a different speed? I couldn't do it this way. The speed is fixed. It would be the derivative, which is 2 times x. Well, what if the speed of the particle isn't 2 times the x coordinate? What if that's not the velocity? And so how can we encode different speeds or different notions of direction and movement along this curve? Well, in order to do that, we're going to have to add something to our situation. We're going to have to throw something else in, add a new variable, add something new in order to get more information. And so the way we do that is we introduce what we call a parameter. And so what is the goal? The goal is to remove the dependency of x on y or y on x and make x and y separate functions dependent on a new variable. We call that new variable the parameter. Typically we use the letter t for our parameter. It doesn't have to be t. And what can this do? It can give us information like direction and speed. And so instead of y equals x squared plus 1, let's consider this set of parametric equations, where x and y don't depend on each other, but instead they depend independently, depend on some new parameter, t. And so let's graph a couple things. Now we have 3 choices, right? We have to pick a t value, and x and y depend on t. And let's just do t from -2 to 2. And in order to get x, well, x is just t itself, so that's not very exciting. Y, again, does not depend on x, it depends on t, so y is then t squared plus 1. So 4 plus 1 is 5, 1 plus 1 is 2, 0 plus 1 is 1, 1 plus 1 is 2, and 2 plus 1 is 5. And so the y coordinates are found independently of x. They're just dependent on t. Now, of course, you're like, well, it is x as well, and that's just because the parametric equation is defined as x equals t. But we still get points, -2, 5, -1, 2, 0, 1, 1, 2, and 2, 5. And if I asked you to graph this set of parametric equations between t being -2 to 2, now we have a notion of direction as we travel along this curve, and we also will get a notion of speed. Speed will be another video. But what we can do now is we'll just plot the points as we normally do. Negative 2, 5, 1, 2, 3, 4, 5. Negative 1, 2, 0, 1, 1, 2, and 2, 5. Where I started at negative 2, I then traveled to this point, then to this point, then to this point, and finally here. And if I start at negative 2 and move forward to 2, if we think of t as like time, then that gives me a notion of now direction. We can add a direction. We're traveling this way along this curve. How could I change that? What if I wanted to travel the other way but draw the same parabola? Maybe do a different set of parametric equations. And so let's consider this set as well. And so if I pick a t value, we'll pick t from negative 2 to 2 again. So negative 2, 0, 1, and 2. What are the x-coordinates? Well, the x-coordinates are now negative t. And so now this is 2, 1, 0, 1, 2. Oh, sorry, 0, negative 1, negative 2. All right, it's negative t. What are the y-coordinates? Well, they're t squared plus 1. So we get 5, 2, 1, 2, and 5 again. And if we draw this out, we start now at the point 2, 5. We move to the point 1, 2, to 0, 1, to negative 1, 2, and negative 2, 5. We draw out the same piece of the parabola that is in the last one. But starting at negative 2, the first point was over here. And I proceeded to move this way along the parabola. So even though I drew the same parabola, I have a different movement along it. I have a different direction in which I'm traveling. I couldn't get that by just giving you y equals x squared plus 1. But by writing it parametrically or giving you a set of parametric equations, now we can give you a notion of direction. It can be very specific. For the time domain negative 2 to 2, I can move forward along this parabola or backwards along this parabola. How do I know that it indeed is this parabola? Well, the first one, we don't really need to do too much. If we think of it, x equals t and y equals t squared plus 1. If we just do substitution, this tells me that t is the same as x. And so we'll substitute that into the second equation. Replacing t with x, we get y equals x squared plus 1. Okay, well, if we do the other one, x equals negative t and y equals t squared plus 1. If I solve the top equation for t, t is negative x. If I then substitute that into this equation, I get y equals negative x parentheses squared plus 1. And squaring the negative just doesn't do anything, and I end up with x squared plus 1 again. So I am sure that they both draw out the parabola x squared plus 1, but they do so in two different ways. How do I encode that information? I do it using parametric equations. So let's go with this a little bit further. We're still going to be looking at the same parabola just to kind of see a point here. And let's look at these three sets of parametric equations on three different time intervals, or three different t intervals. Negative 1 to 1, negative 1/2 to 1/2, and negative 2 to 2. And so we'll label these. I'll call this number 1, number 2, and number 3. And so for the first one, well, let's do negative 1, 0, and 1, x and y. Well, negative 1, 0, 1. It's the same one we had before. So 2, 1, 2. And we'll graph it in a second. Let's look at the second one. X and y. Now we're looking at a time frame that's tighter between negative 1/2 and 1/2. So let's do negative 1/2, 0 and 1/2. The x coordinate is 2 times t. So 2 times negative 1/2 is negative 1. 2 times 0 is 0. 2 times 1/2 is 1. The y coordinate is 4t squared plus 1. So if I square negative 1/2, I get 1/4 times 4 is 1, and 1 plus 1 is 2. Plugging 0 in, I get 0 plus 1 is 1. And 1/2, if I put 1/2 in, I get 1/4. 1/4 times 4 is 1, and 1 plus 1 is 2. And finally, the third. Now we have a little bit longer of an interval, -2 to 2. So let's do -2, -1, 0, 1, and 2. Now we get half of t, right? So so it's 1/2 of t. So we cut everything in half, so we get -1, -1/2, 0, 1/2, 1. And the y is 1/4 t squared plus 1. So now we're cutting everything in a fourth. So in this case, we get 1/4 of 4, which is 1, and 1 plus 1 is 2. Here we get 1/4 of 1, -1 squared. 1/4 of 1 is 1/4, and 1/4 plus 1 is 5/4. Here we get 0, plus 1 is 1. Here we get 1/4, right? 1 squared is 1. 1/4 plus 1 is 5/4. And finally, when t is 2, we get 4. 4/4 is 1, and 1 plus 1 is 2. And so now let's draw out what we get. Well, in the first case, we get that parabola that we started with. We're traveling this way along that parabola piece. In the second case, we also get the same parabola, -1, 2, 0, 1, 2. Traveling that way. And in the last one, we get the, again, same exact parabola piece. -1/2, 5/4. 1/2, 5/4, 1, 2. So again, we get the same parabola piece, same exact parabola piece in all three cases. What is the difference here? Is they all traced it out at different speeds. So you notice here, from -1 to 1, if we think of this in seconds, that's 2 seconds from -1 to 1. And in 2 seconds, we drew out this piece of the parabola. Here, from -1/2 to 1/2, that's 1 second. In 1 second, I drew out that same piece. And so I drew out this twice as fast as the one above it. In this case, I had 4 seconds. And in 4 seconds, I drew out the same piece. So I actually drew it out slower. So this is like my base case. Then the second representation drew it out twice as fast. And this one drew it out twice as slow. Half as fast. That way. And so I drew out the same piece in each case. However, I did it at different speeds. And in all of these cases, if you did the same thing, I'll show you in the second case, for example. They all give me the same parabola. So I just want to show you that we are indeed drawing x squared plus 1. We're not drawing some other random curve. And so let's solve that top equation for t. And let's substitute it in. Right, so we're eliminating the parameter. That's what we call this. So solve for t, plug it in. Now we have a function we've gotten rid of the t variable, right? So we're reintroducing the dependency that we didn't want to begin with. And in doing so, what do we get? X squared over 4. The 4's cancel. And so you get x squared plus 1. And yes, you are indeed drawing the parabola y equals x squared plus 1. In all cases, you can do it with this one as well. So they're all drawing the same parabola. The only difference is they're drawing it out at different speeds. Where if I just gave you this information again, you wouldn't have those different speeds. You just have whatever the derivative is. But I can encode different speeds if I parametrize it differently. So parametric equations allow me to get more information out of a curve. And so let's just get a little bit more practice with this and some different types of parametrizations that we can run into. And this will give us a good start before we then introduce the calculus behind it. Because of course, since we're talking about speed at some point, then we do want to take derivatives. And then comes the question of how do we take derivatives of parametric equations? Given a set of parametric equations, how do we take their derivatives? So let's do another one. Let's just try to draw it out. All right. And let's do t greater than 0. Let's look at this for all time greater than 0, starting at 0. And so let's look at what's happening to the x and y coordinates. Well, at 0, this is undefined, which is why I said strictly greater than 0. But we do have to realize that there's a lot of values between 0 and 1. And so 0 is undefined here. And at 0, the other one, the y is not undefined, it would be 1, right? So we get 1. Okay, well, let's move forward in time. And let's think about 1, right? If we're time 1, then we're the x-coordinate 1. If we're time 2, we're the x-coordinate 1/2. At time 3, the x-coordinate 1/3. And we see that as we move forward in time, the x-coordinate's going to 0. Let's see what happened to the y-coordinate. Well, it's t plus 1. So 2, 3, 4, and blowing up to infinity. And so what does that look like in terms of a picture? Well, at time 0, we're undefined in the x-coordinate, or really infinity, right? When t is 0, this is blowing up to infinity. So we're infinity in the x-coordinate and 1 in the y-coordinate. So it's almost like we have a horizontal asymptote at 1, and we're like approaching infinity, 1, right? I'm going to write this here in this Corbel notation. It's like that first coordinate is infinity, 1. Infinity in the x direction, 1 in the y direction. It's almost like a vertical asymptote, or a horizontal asymptote at 1. And then at 1 second, we are the point 1, 2. I draw. Here. And so I started way out here at infinity, 1, and in 1 second, all of a sudden, I'm here at 1, 2. In the span of 1 second. That was very fast to travel that vast distance from infinity, 1 to 1, 2. And then I go to 1/2, 3. It's curving up like this. So I continue on. And then 1/3, 4. 1/4, 5, and you see the x-coordinate is arbitrarily getting close to 0, so again we have like a vertical asymptote here. And the y-coordinate is blowing up, and so it's looking something like this. And we're traveling in this direction. Now this looks like a piece of a rational function, right? This looks like a piece of a rational function. In fact, it is. We can find it. And so we get this piece starting here and moving up. In the span of 1 second, we traveled an infinite distance from infinity, 1 to 1, 2, and then we kind of slow down a lot and blow up to infinity here. What would this be if we kind of got rid of that parameter? I multiply both sides by t, divide both sides by x. So t is 1/x if I solve this for t. Replacing that or substituting that into the second equation, we get, yeah, sure enough, a rational function, 1/x, shifted up 1 unit. Which is, if I look at t restricted to be positive, we get this piece of that rational function. And so that's the rational function we get. So that's a more interesting example of a parameterization. Why? Because it's, well, you start out at some undefined value, you get somewhere, and then you blow up to infinity, so we have some more asymptotic behavior with this parametric equation. And then another more interesting type of parameterization that we can run into would be maybe something like this. would be, say we have x and y as trigonometric functions like sine and cosine, and I restrict t to be, of course, we have radian measures, so between 0 and 2 pi. And let's see what this looks like. So we pick some t values. 0, I'll pick nice t values, so 0, pi over 2, or actually let's just do, pi over 2, pi, 3 pi over 2, and 2 pi, my nice quadrant angles. Okay, x would be 2 times sine of t, and so sine is 0 at 0, pi, and 2 pi, so these are all going to be 0. And at pi over 2, it's 1, so we get 2 times 1, it's 2. 3 pi over 2, we're negative 1, so negative 2. Let's see y coordinate. Y would be cosine of these t values here, and cosine is 0 at pi over 2 and 3 pi over 2. The other places at 0 were 1, so 3 times 1 is 3. At pi, we're negative 1, so negative 3. And at 2 pi, we are 1, again, so 3. And let's graph this out. Well, at time 0, we're the point 0, 3. 0 in the x, 3 in the y, there you go. At time pi over 2, we're 2, 0. So 2 in the x, 0 in the y. And then 0 in the x, negative 3 in the y. Negative 2 in the x direction, 0 in the y direction. And finally 0, 3. Oh, we're back to where we started, which is why we just go up to 2 pi and not include it, because we don't want to overlap. If we actually trace out what this is, we just traced out, well, not quite a circle, but an ellipse. Remember your conic sections from high school? This is an ellipse centered at 0, 0. And in this case, I am moving clockwise around the ellipse, right? We traced it out this way. Making it counterclockwise, I mean, we could throw some negatives in or switch which one's sine and which one's cosine. But either way, we're drawing it out a certain way. We can start at different place or make it go backwards depending on negatives or which one's sine and which one's cosine. But we drew out an ellipse. And so we can draw out circles, right? Things that aren't necessarily even functions like y depending on x or x depending on y, but just random graphs as parametric equations in terms of functions that we know, like sine and cosine. Now, how do I know that this is an ellipse and not like a rectangle or a rhombus or something like that? Is I could solve this and get rid of the parameter. Now, instead of trying to solve this for t, that would require some arc sine stuff, I'm going to remember something from trigonometry, and that's my Pythagorean identity. I'm going to remember that sine squared. In this case, we'll use t since t is the variable here. Plus cosine squared equals 1. So wait a minute then. Sine here can be written as x over 2. And here cosine is y over 3. And so just replacing that in this equation, we get x over 2 squared plus y over 3 squared equals 1. Get x squared over 4 plus y squared over 9 equals 1. And we know from algebra that this is a standard form for the equation of an ellipse with a minor axis of 2 and a major axis of 3. And so this is an ellipse. Sure enough, it is. And so we can also draw out ellipses. I mean, if we want it to be a circle, we see that if I just change 2 or 3 to be the same number, we'd get a circle centered at 0, 0. If I want an ellipse, I'm just going to change what these numbers are. You notice that 2 and 3 directly correspond to, right, how far you are away from 0 in the x and how far away you are from 0 in the y, right? You're stretching out your circle in a certain way. And so this is another type of parameterization we can run into. But in general, parameterizations, we haven't talked anything with calculus, so it is just very algebra and graphing. It's, it's just a new way to consider functions. So given a time parameter, t, plotting points, looking at what the picture looks like, seeing what the function actually is by getting rid of the parameter. But right now, it's just a lot of algebra, right? So this is kind of our intro. We're not really ready to do some calculus yet. And in the next video, we will introduce now derivatives. We'll talk about how do we take derivatives of parametric equations. And that will be in the next video.